Imagine an AI platform processing something like 100,000 concurrent voice streams.
Right. A massive scale.
Yeah, exactly. So someone is out there negotiating a real estate deal, someone else is getting, live tutoring, and another user is running complex data analytics via voice.
Oh, wow.
And then suddenly, a major fiber optic trunk line gets severed in Ohio. The network just fractures.
It happens way more often than you'd think.
Right. And in a fraction of a millisecond, because a database didn't know how to fail gracefully, the system accidentally double bills 10,000 users and corrupts hundreds of hours of session transcripts.
Yeah, that is a nightmare scenario.
It really is. So welcome back to the Architecture Sandbox. It is Friday, July 17th, 2026, and today we have a very specific, honestly, very critical mission to make sure that catastrophe never happens to you.
Absolutely.
We are locking in the physical reality of the data persistence layer for your real-time streaming conversational AI platform.
And, that scenario you just described, that's exactly what keeps infrastructure engineers awake at night.
I bet.
Yeah, we need to establish right up front that building a platform of this magnitude, it isn't just about spinning up a database instance and, throwing JSON objects at it.
Right. It's way more complex than that.
Exactly. We are talking about how to store, how to scale, and how to retrieve incredibly volatile data across highly distributed systems. And you have to do all of that without the whole architecture just buckling under the immense pressure of global real-time scale.
Okay, let's unpack this, because I think it's tempting to jump straight to the sexy stuff, right? The ultra-low latency audio streaming, the cutting-edge real-time AI processing.
Oh, of course. Everyone wants to talk about the AI.
Right. But we have to start with the foundation, the absolute bedrock of your system. And that means we have to talk about the most critical data first, the money and the keys.
Yeah, before we can even begin to optimize for blistering, sub-millisecond speed, we have to guarantee absolute uncompromising correctness.
Correctness is key.
It is. And that brings us directly to the philosophy of relational databases. This is your classic battle-tested approach to data storage.
The old reliable.
Exactly. You are storing data in very rigid, schema-defined tables, and they're related by specific foreign keys. And you're doing this primarily because you need the ironclad protection of ACID guarantees.
And since we're operating at this level in this deep dive, we don't need to spell out the ACID acronym for you. You already know it's about atomicity, consistency, isolation, and durability.
Right, fundamentals.
Yeah, but what we do need to talk about is the operational cost of those guarantees. Because enforcing ACID in a distributed system, it's essentially imposing a massive latency tax on your infrastructure.
That latency tax is really the defining feature of relational databases. Think about the mechanical reality of a transaction. When your platform processes a billing event, it has to deduct credits from a user's account and simultaneously record a usage ledger for that exact stream.
All at the same time.
Right. To guarantee atomicity and isolation, the database literally has to execute row-level locking. It puts a temporary lock on that user's account balance row.
Oh, so nobody else can touch it.
Exactly. If 3 other concurrent streams for that same enterprise account try to update the balance at the exact same millisecond, the database just forces them to wait in a queue.
Right, so it's like an armored bank truck, or actually, maybe it's more like a train yard switching system. Only one train can occupy a specific segment of track at a time.
That's a great way to look at it.
Because if 2 trains try to enter, one is forced to halt completely until the other clears the track. That prevents a catastrophic collision, or in your case, a double spend. But it entirely kills your momentum.
What's fascinating here is why billing math is the quintessential use case for swallowing that latency tax. A dropped transaction in a chat interface is an annoyance.
Yeah, you just refresh.
Right. But a dropped transaction in billing is a financial disaster. If the system crashes midway through writing the ledger, the relational database relies on its write-ahead log, or the wall, to basically roll the entire multi-step process back upon reboot as if it never occurred.
So you never end up in a corrupted, half-finished state.
Never.
So mapping this to your sandbox, this is exactly why your platform's control plane belongs in a strict relational database like Postgres. Your user accounts, your API keys, and absolutely your billing metrics, they all require that track switching logic.
They absolutely do.
You need absolute correctness and security over raw speed, and you're willing to pay the CPU and latency penalties to get it.
But, and this is a big but, that heavy locking mechanism brings us to an unavoidable bottleneck. Once you move past the control plane and into the media plane, That track switching logic completely breaks down.
And this is where the architecture has to forcibly mutate, because if you have 100,000 users streaming live conversational audio, you can't have those AI streams waiting in a lock queue.
No, the latency would be unusable.
Right. The conversational AI loop demands responses in under a second. The database just cannot be the bottleneck. So we have to trade the rigidity and safety of Postgres for raw, unadulterated speed. We move to NoSQL.
Yeah, NoSQL operates on a fundamentally different philosophy. It says, let's bypass the heavy ASIC guarantees, drop the rigid schemas, and prioritize lightning-fast ingestion and retrieval.
Speed over everything.
Exactly. But NoSQL isn't a single tool, right? It's a category. For your live session state, you're going to rely on a key value store like Redis or DynamoDB.
Mechanically, a key value store achieves that sub-millisecond speed by bypassing standard disk I/O entirely.
That's the secret sauce.
Yeah. Redis, for example, operates entirely in memory, like in the RAM. It's basically just a giant blazing fast dictionary. When a user connects to a voice node, the node writes the connection state, the routing data, and the real-time telemetry straight to RAM.
And because it's operating in RAM, you introduce a new mechanical challenge, which is memory limits.
Right, RAM isn't infinite.
Exactly. When RAM fills up, the database doesn't just crash. It executes eviction policies. It looks for the least recently used data, the LRU, and silently purges it to make room for the new data.
Wow.
Yeah, so you are intentionally accepting data loss for transient data to keep the system moving at the speed of human conversation.
So that's the live telemetry. But the actual output of your platform, the procession transcripts generated by your STT streamer, those really don't fit well in a key value store.
No, they're too complex for that.
Right, they fit perfectly into a document store like MongoDB. Instead of rows and columns, you're storing unstructured JSON or YAML objects.
Yeah, a document store is perfect there.
Because a transcript is essentially a deeply nested JSON object. It has varying metadata depending on how many speakers were identified or what language was spoken. A document store just swallows that nested payload whole instantly without needing a rigid schema.
It's the ideal structure because the shape of the data is inherently unpredictable. One transcript might have extensive timestamps and sentiment analysis tags attached to every single word, while another might just be a raw block of text.
I mean, we also have to mention graph databases like Neo4j, briefly, which are optimized for relationships, but for the transcripts, document store is the way to go. But wait, I have to push back here.
Okay, go ahead.
If NoSQL is so blazing fast and MongoDB can handle massive volumes of completely unpredictable data structures, why are we drawing this arbitrary line and keeping Postgres at all?
That is the big question.
Right. Like, why not just dump everything, including the billing data, into one giant NoSQL cluster and save ourselves the operational nightmare of maintaining two completely different database paradigms?
Oh man, that is the siren song of NoSQL. And giving into it almost always results in a catastrophic data migration a year later.
Really? A catastrophe.
Yeah. Yes. Flexibility breeds chaos if it's applied to highly structured data. If you put your billing data in a document store, there is absolutely nothing at the database level enforcing that every single record has a mandatory validated schema.
So if an application code update introduces a bug and suddenly starts writing billing records that are entirely missing a currency field?
The NoSQL database would just happily accept it. It just assumes you wanted to change the document structure.
Oh, I see.
Yeah, and then weeks later, when your finance team tries to run a quarterly revenue report, the query just breaks because thousands of records are suddenly missing critical math fields.
That sounds like a bad day at the office.
A terrible day. Postgres, on the other hand, enforces data integrity at the lowest possible level. It would reject that malformed write instantly with a fatal error, saving your revenue data. Different data types just demand different tools.
That makes perfect sense. The friction of Postgres is actually a feature, not a bug when it comes to money. So we've got Postgres handling the control plane, Redis handling the live state, and MongoDB swallowing the transcripts. But what happens when the cache gets overwhelmed? Like when your marketing team succeeds, the platform goes viral, and suddenly that Redis cache and your Postgres primary are getting absolutely hammered. We need to scale.
Scaling distributed systems relies on three completely orthogonal techniques. And the reality of truly large-scale architecture is that you must use all three simultaneously.
All three at once.
Yes. Let's look at the mechanics, starting with indexing. Indexing makes a single machine significantly faster by providing sublinear lookups. Under the hood, it uses data structures like hash maps or B trees, so the database can jump straight to the data block it needs instead of, scanning every single row on the hard drive.
But there is a brutal trade-off there. Maintaining that index isn't free.
No, it's very expensive.
Every time a new billing record is written, the database doesn't just drop the data on the disk and move on. It has to pause, recalculate the B-tree structure, resort the index nodes, and update the pointers before it can actually confirm the right operation to the user.
You are intentionally trading write speed to buy read speed. If you try to index every single column in your database, your reads will be instant, sure, but your system will grind to an absolute halt every time it tries to insert a new row.
So for your sandbox impact, you are going to heavily lean on composite indexes in your Postgres control plane to protect your API queries from triggering full table scans, but you have to be surgically precise about which columns you index.
Right. You can't index everything.
Now, if indexing makes one machine faster, the second technique, replication, makes your data safer and read scalable.
Yeah, replication introduces a completely different mechanical reality.
Yeah.
By copying your data across multiple replica nodes, you eliminate single points of failure.
Which is critical.
Exactly. You write the primary database, and it asynchronously streams those changes to the read replicas.
But that introduces the headache of replication lag, right? Like, if a user buys credits, the primary database updates instantly. But if they immediately click over to their billing dashboard and that dashboard is reading from a replica in a different data center, the copy might not have finished yet. The dashboard shows 0 credits.
Which is exactly why you have to carefully route traffic. You utilize read replicas to absorb all your heavy dashboard traffic, but any operation that relies on immediate, guaranteed state must read from the primary.
Makes sense. Now, the third technique is partitioning, or sharding. And I think the best way to visualize the mechanics of partitioning is to think about setting up VIP lanes at a massive music festival.
Oh, that's a good analogy.
Thanks. Yeah, if everyone tries to go through the main gate, it's a total disaster. So partitioning is basically ripping the book into chapters and handing different chapters to different people. Or, going back to the festival, it's splitting the traffic and the data across completely different physical servers based on a key.
That tenant isolation is critical for your business model. You are going to have enterprise customers who are paying top dollar, and you cannot have them sharing compute or database infrastructure with your free tier users.
Exactly. You partition your infrastructure so that enterprise customers run on completely isolated database shards.
Keeping them separate.
Right. That way, if a sudden massive spike of noisy free tier traffic hits the platform, it is physically impossible for them to chew up the CPU cycles and memory that your enterprise clients are paying for. You protect their strict sub-800 millisecond latency budget by walling them off entirely.
If we connect this to the bigger picture, you start to see the elegance of distributed architecture. By layering precise B-tree indexing to speed up lookups, strategic replication to ensure safety and absorb read traffic, and physical partitioning to break up massive data sets and isolate your VIP tenants, you create a system that can theoretically scale infinitely.
Infinite scale sounds nice. But even with all of that perfect scaling, we still have to face a harsh physical reality.
Hardware fails.
Networks inevitably fail. Fiber optic cables get cut by construction backhoes. Data centers lose power. Routers go down. When a network partition happens and your data centers can no longer talk to each other, how does the system decide what to do?
This brings us to a foundational concept in computer science, Eric Brewer's CAP theorem.
CAP.
Yeah, CAP stands for consistency, availability, and partition tolerance. The theorem dictates a harsh mathematical reality. During a network partition, a distributed database physically cannot guarantee both consistency and availability. It must choose only one.
Here's where it gets really interesting for your platform, because you literally have to design a database with a split personality depending on the data type it's handling.
A split personality, yes.
Let's look at the mechanics of the two options. The first choice is CP, which is consistency over availability.
Right. In a strictly CP system, if the network fractures, the database will actively refuse to serve requests.
It just shuts down.
Basically. It will return a hard error rather than risk serving data that might be stale or processing a write that might conflict later. It prioritizes the absolute truth over user experience.
The other option is AP, which is availability over consistency.
In an AP system, the database stays up and serves the request no matter what. It acknowledges that the data it's handing to the user might be out of date, or that the write it's accepting might cause a conflict when the network heals, but it absolutely refuses to go offline.
Mapping this to your sandbox impact, this EAP theorem is the single most critical lens for your data layer. Let's look at your Postgres control plane. It is strictly configured for CP, consistency over availability.
Right, for the billing.
Exactly. Think about a live API quota check. If a user is trying to start a massive, expensive new AI stream and the billing nodes can't sync due to a network partition, that API call must fail. You would rather throw a service unavailable 503 error at the user than authorize a compute-heavy AI call on stale billing data and just bleed money.
Contrast that with your orchestrator, the system handling the live, real-time audio session telemetry in Redis. That is strictly AP. Availability over consistency.
So it stays up.
It has to. If there's a momentary network blip between nodes, you would much rather serve slightly stale state data to the dashboard. Maybe a user's connection status lags by a few milliseconds, rather than throw a hard error and completely collapse the real-time audio loop.
Because dropping a live phone call or a live translation because of a microsecond network jitter is just the worst possible user experience.
It ruined the product.
It's a beautiful illustration of architectural pragmatism. You are deliberately choosing CP for your money and AP for your real-time user experience. Okay, so we've handled the rigid text, the blazing fast telemetry, the unpredictable transcripts, and the billing. But we have a massive elephant in the room.
Oh, the audio files.
Where do the raw audio files go? The actual massive WAV or MP3 recordings? Because relational and NoSQL databases would absolutely choke if you tried to shove media files into them.
Oh, they wouldn't just choke. They would physically fragment and corrupt. Binary large objects, which we call blobs in the industry, like raw audio, video, and disk images, they do not belong in a database.
Not at all.
Shoving a 50-megabyte audio file into a Postgres row bloats the table, destroys the caching mechanisms we just talked about, and fundamentally ruins the B-tree index structure. Blobs belong in an object store.
Right. An object store completely bypasses the traditional file system hierarchy. You don't have tables, you don't have documents, and you don't even have folders in the traditional sense. You just have flat buckets.
Hot buckets.
You take an audio file, generate a unique cryptographic hash for it, and drop it into the bucket. You access it via simple HTTP REST API calls, and crucially, it gives you immutable versioning.
Immutability is key here.
Once that audio file is written, it physically cannot be altered. If a user edits the audio, the system doesn't change the file. It uploads an entirely new version and updates the pointer.
And because these media files are huge, and they accumulate at a terrifying rate, object storage introduces the concept of lifecycle tiering. Cloud providers offer specific storage tiers based on access frequency and retrieval latency.
Right, like hot and cold data.
Exactly. You have your hot tier. This is for immediate access, where latency is measured in milliseconds, but it carries the highest per gigabyte cost.
Then you step down. Warm, cool, and finally, cold storage, like Amazon Glacier. Cold storage is for long-term legal archiving.
The cheap stuff.
Exactly. The cost drops at pennies on the dollar, but the mechanical reality of retrieval changes entirely. If you want a file from cold storage, you don't get it instantly. You issue a retrieval request, and it might take hours for the cloud provider's automated tape drives to physically mount and fetch that data.
The most powerful aspect of this layer, however, is standardization. A lot of platforms start in the cloud, but eventually the bandwidth, egress, and storage costs for raw audio get so astronomical that they want to pull it in-house to their own bare metal servers.
Wait, so if you do that, pulling it in-house, doesn't that usually mean rewriting thousands of lines of application code?
Not anymore.
Really?
Yeah. The object store abstraction has been entirely standardized around the S3 API. S3 isn't just an Amazon Web Services product anymore. It has become the universal language of object storage.
Oh, wow.
Solutions like Minio or Ceph allow you to run completely S3-compatible environments on your own on-premise hardware. Your application code literally doesn't know the difference.
That's incredible.
It just fires off an S3 API call. Whether that call resolves to a massive AWS data center or a custom server rack sitting in your basement, the code remains identical.
That is massive for the future-proofing of your platform. So locking in the sandbox impact for this final layer, this is your media plane. All the raw uploaded audio from your users and the rendered call recordings generated by your conversational AI will be stored as immutable objects in an S3-compatible store.
Exactly right.
The hot recent audio stays in standard storage, but you are going to apply strict lifecycle rules. After 90 days, the object store will automatically tier older audio down to cold storage for long-term retention, massively optimizing your burn rate.
It creates a perfectly balanced ecosystem.
Yeah.
The fast data stays fast, the rigid data stays rigid, and the heavy data stays cheap.
Incredible. Well, let's pull all of this together. We have formally mapped out the data persistence boundaries for your architecture. It is a masterclass in accepting trade-offs and using the right tool for the job.
It really is.
You have the heavy track switching logic of Postgres, providing strict CP control for your billing and accounts. You have the RAM-based memory evicting speed of Redis, providing sub-millisecond AP state for your real-time orchestrator. You have document stores absorbing your wildly unpredictable JSON transcripts. And you have flat, immutable S3 buckets handling the heavy lifting for your massive audio blobs.
The physical reality of your data layer is locked.
So, as you look at your blueprints, what do you want to tackle next? Do we draft a formal architectural decision record, like an ADR, detailing exactly how you are configuring those cap theorem trade-offs? Or would you prefer to mathematically map out the exact timing of those S3 storage lifecycle rules to project your future infrastructure costs?
This raises an important question, though. A highly complex thread you need to pull on before you finalize this architecture.
Okay, what is it?
You've perfectly organized your data into these highly specialized, mechanically distinct, silo-strict ACID Postgres for billing, volatile RAM-based Redis for state, completely detached immutable S3 for audio. But here is something for you to mull over.
I'm listening.
When a user inevitably invokes their privacy rights and clicks "delete my account," how do you guarantee that all of these completely disconnected systems, operating at fundamentally different speeds with completely different consensus rules, successfully agree to wipe that user's existence from reality without leaving ghost data behind?
The distributed delete. It's the ultimate test of a fragmented data layer. That is a massive, complex logistical challenge to ponder. Well, thank you so much for joining us in the Architecture Sandbox today. Take some time to think about the friction between those disconnected systems, and we will see you next time as we keep building out the platform.